This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on area of triangles. We have three triangles here, and I want you to notice this first one is a right triangle. And you can think of it as half of a rectangle, whose width is b and whose height is h. If the rectangle would have area BH, the triangle is half the rectangle, and would therefore have area half BH. So that's the case here, and the reality is these two cases both have area that is also 1/2 base times height. So that's our fundamental concept we're going to use to find the area of a triangle. 1/2 the base times the height, and the height is perpendicular to the base. And notice with this case here, the height doesn't even have to be inside the triangle, it could be outside the triangle. So we're going to start with what I call an SAS case, side, angle, side. We have two sides with an included angle. We want to find the area of this triangle. I'm going to think of 8 as the base, then the height will be perpendicular to 8. So the height will be here. We want to find the area of this triangle, which will be half base times height. Half 8 times this value, height. How are we going to find that? Well, the sine of 60 degrees is opposite over hypotenuse. So if you look at this little triangle, the opposite of 60 degrees is height, and the hypotenuse is 5. So the sine of 60 degrees is height divided by 5. So we can solve for height. 5 times sine 60 degrees would equal height. So I have root 3 over 2 is height divided by 5. 5 times root 3 over 2 is the height. Well, if that's the case, now we know the base and we know the height. We can put them together to find the area of the triangle, remembering the area of a triangle is base times height. So the 5 root 3 over 2 is the height, and of course the base is 8. So if area is 1/2 base times height, area would be 1/2 8 times 5 root 3 over 2, which would give us a half of 8 is 4. 4 divided by 2 is 2, times 5 is 10. 10 root 3 is the area. Now, if this had been 8 inches and 5 inches, the height would be in inches, then our area would be square inches or inches squared. Area is always in square units, something to keep in mind. So that was our first example of an SAS triangle. Let's take a look at another one now. So I have two sides. This side is 5. This side is 4, and the included angle in between them is 150 degrees. Now, this is an obtuse triangle. So the question is, where is the height? The height has to be perpendicular to the base. So if I call this the base, if the base is 5, the height perpendicular to the base would be here. So how do we find that distance? What's going to work? Well, again, the area is 1/2 the base times the height. And the base in this problem, of course, is 5. And the question is then, how do we find the height? How are we going to do that? So let's go ahead and construct another triangle from here up to there. And this side will be the height of this big triangle. So the height, again, perpendicular to the base, this is a right angle, dropped down from this corner to this extended. The angle here is 150 degrees, so the angle here would be, the supplement would be 30 degrees. The quadrant 2 angle. But I just want you to notice something. The sine of 150 degrees is, that's quadrant 2. 30 degrees is quadrant 1, that's its reference angle. They have the same sign, S-I-N. So again, the base is 5. How do we find the height? In this case, opposite over hypotenuse. Opposite of 30 degrees is the height, and the hypotenuse is here, which is 4. So the sine of 30 degrees is height over 4. But just to notice something, the sine of 150 degrees is the same as the sine of 30 degrees. So you really could say sine of 150 degrees is height over 4 as well. But I prefer this model because I think it's easier to see where it comes from. Sine of 30 degrees is, of course, half. So 1/2 is height divided by 4. If I multiply both sides by 4, I get 2 is the height. Well, we want to go ahead and find the area of this triangle, the 5, 450 degree triangle, the SAS triangle. 1/2 base times height, 1/2 5 times 2, which of course is simply going to be 5. Again, square units. If 5 and 4 were meters, the area would be 5 square meters, or 5 meters squared. Area is always measured in square units. So we can find the sine of the given angle, or in this case, the sine of its supplement, to determine the area of an SAS triangle. The next example I want to look at is an SSS triangle. So I have three sides. I have A, B, and C. I don't have any angles. You'll recall that if we were going to solve an SSS triangle, we would use the law of cosines. Well, here we have another sort of model that we're going to use to find the area of this triangle. We're going to start with this notion of the semi-perimeter. Now, the perimeter is how much fence you would put all around this triangle. The perimeter would be A plus B plus C. So the semi-perimeter would be half of A plus B plus C. And this is going to be important for us as we determine the area of this SSS triangle. We use a technique called Heron's formula, sometimes called Hero's formula, which is based on the semi-perimeter S. So Heron's formula tells us that the area is the square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. If we put all that together, we can find the area of that triangle. So our example, we have an A of 5, a B of 12, and a C of 13. Three sides, no angles, SAS case. If I'm finding the area of an SSS triangle, I will use Heron's formula. But the first thing I need is the semi-perimeter. So we're going to add up 5 plus 12 plus 13, semi-perimeter, and then divide by 2. 5 plus 12 plus 13 is 30, divided by 2 is 15. Half the perimeter is 15. So 15 will be used as we compute the area of this rectangle. So there's our formula. S is 15. S minus A will be 15 minus 5. S minus B will be 15 minus 12. S minus 13 will be, S minus C will be 15 minus 13. So there's all of the substitution. 15 minus 5 is 10. 15 minus 12 is 3. And 15 minus 13 is 2. Multiplying that, we get A is the square root of 900. What times itself is 900? And the answer is 30. 30 square inches, square feet, square meters, whatever our units are, the area would be 30 square units. But there's something a little interesting about this example. We have A is 5, B is 12, and C is 13. 5 squared is 25. 12 squared is 144. 25 plus 144 is 169. It tells us something. 5 squared plus 12 squared is 13 squared. If that happens, we know that we have a right triangle. So let's go ahead and construct that right triangle and see if we get the same area as we had obtained by using Heron's formula. 5 here, 12 there, 13 here. Largest side opposite the right angle. The area of a triangle is 1/2 base times height. 1/2 12. The base times the height here perpendicular to the base. Well, it's the side of the triangle. In the case of a right triangle, the height is 5. So 1/2 12 times 5 gives us what? Gives us 30 square units again, which is exactly what we had obtained by using Heron's formula. So let's take a look at one more example. This will be another SSS triangle. So we have A is 5, B is 7, and C is 8. Well, is this a right triangle? Does 5 squared plus 7 squared equal 8 squared? 25 plus 49 is not 64. It's 74. So it's not a right triangle. I'm going to go ahead and appeal to Heron's formula to find the area. So step 1 is to find the semi-perimeter. A plus B plus C divided by 2. 5 plus 7 is 12, plus 8 is 20, divided by 2. It gives me a semi-perimeter of 10. Then the area is the square root of S times S minus A times S minus B times S minus C. S is 10. This will be the square root of 10 times 10 minus 5 times 10 minus 7 times 10 minus 8. 10 minus 5 is 5. 10 minus 7 is 3. 10 minus 2 is 8. 5 times 2 is 10. 10 times 3 is 30. Times 10 is 300. The area is the square root of 300. Root 100 times root 3. Root 100 is 10. 10 times root 3. And the area of this SSS triangle is 10 root 3 square inches, square meters, square centimeters, whatever units you were using. And that will conclude this lesson.